there, and welcome to this explainer. Today, we're uncovering the absolutely fascinating secret history of artificial intelligence. Now, I know it's super easy to look around today and think AI is just this sudden modern invention, right? Like it's just a product of the last few years. But as we're going to see, it's actually the result of a heroic, decades-long journey of an idea. The story of the thinking machine doesn't start in some sleek modern data center. It begins way, way earlier with a really profound curiosity about the nature of intelligence itself. Okay, let's set the scene. Picture this. It's the 1940s. The world is in the middle of a massive technological upheaval. You've got a landscape completely dominated by vacuum tubes, punch cards, and the raw, clunky machinery of the Second World War. But amidst all that rigid, heavy hardware, a really radical question began to flicker in hushed laboratories. What if we could build a machine that actually learned? Not just a machine that blindly followed a strict set of instructions, but one that could organically adapt. Because you see, the early computers of that era, giants like the ENIAC and UNIVAC, were monumental achievements for sure, but they were essentially just pre-programmed glorified calculators. They crunched numbers brilliantly, but they had literally zero independent thought. On the flip side, you have the human brain. It's squishy, it's magical, and it's packed with 100 billion neurons, just effortlessly adapting and predicting every second of the day. The early pioneers of AI looked at this massive gap between those dumb wartime calculators and the wonder of human cognition, and they thought, we want to engineer an artificial mind. To pull this off, they looked right at the biological blueprint of the brain. The absolute fundamental unit of our cognition is the biological neuron. And honestly, it's an elegantly simple little device. It receives signals from other neurons through these branches called dendrites. If the incoming signals hit a certain combined threshold, boom, the neuron fires an electrical impulse down its axon to pass the message along. That incredibly simple fire or don't fire threshold, that is the very foundation of how you and I perceive the world. So right around 1943, a neurophysiologist named Warren McCulloch and a brilliant young mathematician named Walter Pitts decided to take that biological squish and translate it into mathematical logic. They proposed the very first artificial neuron. It was a simple binary switch that received multiple inputs, and each input had a different weight, or level of importance. If the sum of those weights crossed a certain threshold, the switch turned on. They actually proved that networks of these mathematical switches could, theoretically, perform any logical function. Now here's the catch, and it's a big one. McCulloch and Pitts had a really cool theoretical switch, but it couldn't actually learn on its own. It needed a missing piece. Enter psychologist Donald Hebb in 1949. He observed this fundamental biological rule: neurons that fire together, wire together. Meaning, if two neurons activate at the same time over and over again, their connection gets physically stronger. This biological observation was a total game changer. It gave engineers a theoretical pathway. If an artificial network could just gradually adjust the weights of its connections based on experience, it could actually learn. While the hardware folks were busy tinkering with neurons, software pioneers like Alan Noel and Herbert Simon at Carnegie Mellon were taking a different route. In 1956, they created the logic theorist. This program famously shifted away from just brute force calculating and used goal-oriented strategies to successfully prove mathematical theorems. It was a brilliant leap forward in computing, no doubt about it, but it was mimicking human reasoning through top-down written code, rather than actually mirroring the messy, brain-inspired biological networks that the true neural network pioneers were dreaming of. Which brings us to part one of our story, the first triumph, Rosenblatt's Perceptron. Let's jump to 1957. Over at the Cornell Aeronautical Laboratory, Frank Rosenblatt took all those theoretical ideas and built an actual physical machine, the Perceptron. This was a working demonstration of an artificial mind, complete with a learning algorithm. It used what we call supervised learning, basically a trial and error feedback loop. It would guess a pattern, like trying to recognize the letter A or a picture of a dog, then it would check the correct label. If it messed up, its internal algorithm would automatically tweak those connection weights to fix the error for the next time. It literally learned how to recognize visual patterns. The excitement was absolutely off the charts. The public, the press, everyone was hyping up the Perceptron as the dawn of true thinking machines. But, a nagging question was floating around among the researchers. Could this simple, single-layer network truly solve any problem? Well, right at the peak of all this massive public hype, a devastating mathematical roadblock was about to crash the party and derailed the entire movement. In 1969, two prominent MIT researchers, Marvin Minsky and Seymour Papert, published a book that rigorously tore into the perceptron. They elegantly and mathematically proved that Rosenblatt's single-layer machine had a fundamental flaw. It couldn't solve something called the XOR, or exclusive OR problem. The XOR problem is just a simple logic puzzle where a machine has to choose either or, but not both. But because the single-layer perceptron relied on drawing a simple straight line to separate data, it was mathematically impossible for it to process this nuanced logic. It hit a literal, impenetrable mathematical wall. And man, the fallout from this proof was devastating. It was basically perceived as a death knell for neural networks. Funding dried up almost instantly. The public, who had just been totally amazed, completely abandoned the dream. The field of AI entered this dark, freezing period that became widely known as the AI winter. The whole concept of a neural network was essentially exiled from mainstream computer science. But that leads us to part 2, the resurrection and the tinkerers in the dark. You see, the story of the thinking machine definitely doesn't end in the winter. Down in the trenches during the 1970s and 80s, these incredibly dedicated underdogs kept the embers burning in quiet academic labs. They knew the single-layer perceptron had limits, but they believed the core idea was still solid. Think of it like this. A single-layer network is essentially like a group of isolated decision-makers getting completely stuck when they can't agree on a complex problem. The obvious conceptual fix was to add multiple hidden layers of artificial neurons so they could team up. But practically, figuring out how to program a machine to efficiently correct its own errors across multiple hidden internal layers was completely baffling. And that brings us to the breakthrough that changed everything: backpropagation. Discovered independently by researchers like Paul Werbos, David Rumelhart, and Geoffrey Hinton, this incredibly elegant algorithm worked backwards. The machine makes a guess. It notes the final error. But instead of just getting stuck, it sends that error backwards through all those hidden layers. This allows every single layer to refine its internal workings. Thanks to backpropagation, these networks finally, and successfully, crushed the dreaded XOR problem. And what's wild is that this multi-layered approach is absolutely profound because it directly mirrors our own human biology. Just like your own visual cortex, a multi-layer network extracts features sequentially. The first layer detects basic edges. The second layer combines those edges into simple shapes. The third layer combines those shapes to recognize whole objects. By passing data through these layers, the network creates a literal hierarchy of understanding. It turns abstract math into biological perception. So now we reach part 3, the modern awakening and unleashing the algorithms. For decades, pioneers like Geoffrey Hinton, Jan LeCun, and Yoshua Bengio, the guys we often call the godfathers of AI today, kept quietly refining these complex algorithms in the dark. They were just waiting for the environment around them to catch up. Which brings us to the ultimate plot twist of this explainer. The modern AI explosion only happened because 2 totally unexpected factors collided. First, the internet exploded, providing massive datasets, the insatiable fuel of information these networks desperately needed to learn. Second, video game GPUs. It turned out that the exact graphics chips designed to render your favorite video games were the perfect parallel processing engines needed to run complex deep neural networks. Who would have thought gaming would save AI, right? When you take a step back and look at this 80-year timeline, you realize pretty quickly that this is no overnight success story. From McCulloch and Pitt's theoretical artificial neuron in 1943, all the way to Rosenblatt's working perceptron in the 50s, enduring the crushing AI winter of 1969, only to be miraculously resurrected by backpropagation in the 80s, the deep learning tech that we completely marvel at today, it was built on over 80 years of relentless, stubborn persistence by engineers who just refused to give up on their vision. So, I'll leave you with this fascinating thought to chew on. If a few simple mathematical switches, originally inspired by the squishy biology of our own brains, can eventually learn to see, to recognize objects, and to master complex patterns, what is the ghost in the machine going to learn to do next? The future of these learning machines built on such humble and resilient beginnings is vast, uncharted, and honestly, incredibly exciting. Thanks so much for exploring this journey with me, and remember to never stop questioning how the world around you actually works.